Alright, so we are continuing our lesson from yesterday. We're looking at radicals, simplifying radicals, and in this case we're simplifying radicals with fractions. Remember, we don't like fractions as our radicands, so we have to split up our numerator and denominator into two separate radicals. So the first one would be square root of 23 over square root of 9. Since 23 can't be broken down any further, it's just the square root of 23 over 3. So here are the answers for this slide. If you're watching it on video, make sure to pause it and give it some time. Try these problems, and then here are the answers. Remember, with that negative, you want to keep it on the outside. We have a perfect square, number 7, on both the numerator and denominator, as well as number 8. The numerator has a 4, which is a perfect square, an x squared, which is a perfect square, and a 64, which is also perfect square. Now notice that on number 8, if you didn't quite get that, you probably didn't reduce all the way, and you want to reduce your fractions all the way. So 2 over 8 simplifies to 1 over 4. Well, because 100 is a perfect square. If you take the square root of 17, you still get 17, square root of 17. If you take the square root of 100, you get 10. So again, just to write it down, just so we're reminded here, for number 6, I split the numerator and denominator into separate radicals, like so. I should not have to make a factor tree for any of my perfect squares. The first one is not a perfect square, but I can't break it down with a factor tree, so I'm going to leave it alone. The second one is a perfect square, and that's just 2. Any other questions? All right. Pull out your worksheet from yesterday. Hopefully you have it finished. All right, I assigned a worksheet yesterday. Here are the answers on this recording so you can check them yourself. Feel free to pause the video if I go too quickly. So yesterday we were dealing with square roots. One thing to remember about square roots is it has an implied index of 2, and we often don't write it. So when I write this, I know I'm taking a square root. I don't have to include that index of 2. I can, but I don't have to. And I don't expect you to as well. Now, any other indices, we have to include them so I know that you're taking a cube root, for example, with a 3. When you're taking a 4th root or a 5th root or a 6th root, etc. Now, last time I briefly mentioned that, at least I think I did, if not, I'll mention it again here, but we don't like to deal with negatives and square roots, because essentially, what is the square root asking us to do? Well, if we look at the square root of 100, we get 10. Why do we get 10? Because 10 times 10 is 100. Now, it gets tricky with negative numbers, because with square roots, of course, you're taking a number times itself. Right? Well, I can't take, for example, the square root of negative 100, because that's not going to be negative 10 times negative 10, because that's a positive 100. Okay? That's not going to be 10 times 10, because that's a positive 100. Okay? Now, when we have a cube root, that changes. I can have a negative, right? Because if I have a negative times a negative, that's a positive, but then times another negative, what do I get? A negative, right? So for example, if I was taking the cube root of negative 8, I would get negative 2, because negative 2 times negative 2 is positive 4, times negative 2 is that negative 8. Right? Remember, these are inverse operations. So when you're cubing things and when you're cube rooting things, they undo each other. So all that is to say, like on this first one, If it's a cube root, all I would do is take the negative output so as not to confuse you, because you know this is possible. It's not going to be an imaginary number, and just simply write the negative output. So, how is this different than what we did yesterday? Well, instead of groups of 2, what do you think we're going to look at? Groups of 3, exactly. So we're going to break this down. We're going to use our divisibility rules. We know it's divisible by 2 because it's even. Is it divisible by 3? No. How do you know? The sum of the digits is 11. Is 11 divisible by 3? No. Is it divisible by 4? Yes. How do you know it's divisible by 4? The last 2 digits are divisible by 4. 28. Is 28 divisible by 4? Then the whole thing is divisible by 4. You see how those help? So now you can set up a factor tree. Instead of using 2, you can use 2. I'm not saying that's wrong. But it just kind of helps you go a little bit faster. So when you take that and you divide it in your calculator, you get 32 and 4. You get 32 and 4. 4 breaks down to 2 and 2. 32 breaks down to 8 and 4. 4 and 2. 2 and 2. 2 and 2. So even though we didn't even use 2, we still have quite a large factor tree. So we still have that negative on the outside. And let me erase these little side bits here. And we're going to do exactly what we just did, but we're going to circle roots of 3. The negative, and then write all my primes. And you could, if you wanted to, write them as 2 to the power of 3 and take those out if you want to, but I'm not going to. So 2 times 2 times 2. And I like to, if I have a large factor tree, just cross them out so I know which ones I took care of. And then you have another 2 times 2. And another 2 times 2. Of all my prime factors. Again, if you wanted to, you could instead rewrite it like this, just to help you out, so you're not writing too many 2's. You could say 2 cubed, that's 1 set of 3's, and then 2 cubed, and then times 2. And you'll see that you can take how many groups of 3 out. One group of 3 and another group of 3, right? So now, our final answer would be negative, and then I took one group out. You still only take one out. One survives. A little prison escape then. And then you take another one out. And then you're left with the 2 on the inside. So what is the simplified t? Negative 4 with 2. Jeff, any questions about that? Yes.
Is the only difference you're just taking groups of 3 out?
Yeah, 2 things you need to know about cube roots. Groups of 3's, and it's okay to have a negative on the inside. If you have a negative on the inside with a square root, right now you don't know how to deal with that because you don't know how to deal with imaginary numbers yet. But with cube roots it's okay, because we talked about when you get groups of 3 you'll get a negative. So yeah, I mean it's not much of a difference other than different groups you're taking out. Okay. Let's look at one more here on this page. And again, you're tackling it in the same way. So if you want to go ahead and start that one, you can. But I'm going to show it on the board. I'm going to go ahead and erase this. Unless, does anyone need it up still? Let's look at the next one. I'm going to start with 5 because I know that 5 goes into 125 25 times. And I always make this mistake. Make sure when you're doing cube roots that you remember the index. I always did that when I was in school, and I still sometimes do that. That index is important because you're cube rooting something. So with 125, that breaks down to 5 and 25, and that breaks down to 5 and 5. So I have a perfect cube, right? So I can just take out a 5. Well, I still have x to the 7, so I'm going to do what I did yesterday. I'm just going to say how many groups of 3 can I take out? How many groups of 3? 2. With how many left over? 1. Right. So I can take out 2 groups of 3 with 1 left over. So 2 groups of 3 would be x and x. That's x squared. With 1 left over. Or you can, of course, write them all out. X times x times x. X times x times x times x. 2 groups of 3, 1 left over. Questions? Is 216 divisible by 3? Is it divisible by 9? Yeah, it is. So I'm going to go ahead and make a factor tree with 9. Okay. Okay. Okay, so it's divisible by 9. I'm going to make a factor tree with 9. When you divide, you get 24 and 9. So 216, I've got 24, and I've got 9. I've got 3 and 3. Those are primes. 24, I can do 12 and 2. That's 6 and 2, and that's 3 and 2. So once again, I'm going to make my square root, or my cube root. See, I do that. Cube root. Now, what am I doing? In my head, I already know that I can split this up into 2. The cube root of y divided by the cube root of 216. So I'm already just looking at the cube root of 216. Because the cube root of y is just going to stay the cube root of y, right? There's no way I can break that down into groups of 3 and simplify it. It's already simplified. So I already know at the top, the numerator is going to be the cube root of y. The bottom, we're going to just 2, cross it off, under 2, under 2, 3, 3, and 3. And then simple groups of 3. This turns out to be perfect cubes here. You've got 1 group of 3, 1 group of 2, and you just get 6. So it goes on the bottom. 6. And I would say, since you have a calculator, I would double check and see if it is a cube, if it is a perfect cube. So take 216 on your calculator, raise that to the 1/3. You'll get 6. Now you can't do that with everything, obviously. You'll get decimal, and I will tell you right now, if you give me a decimal, you'll get it wrong. You need to give me a simplified radical. Some of those radicals are perfect cubes and perfect squares, so that's perfectly okay if you took this in a calculator and just get 6. But any of the ones that you will get decimals on, I expect you to simplify that radical and give me that answer. Okay. Any questions on that top one? Okay. The bottom one. I want you to walk me through this one. How can you rewrite this one with a fraction? What did I say to do when you have a fraction as a radicand, first of all? Separate them. Right. Separate them into two separate radicals. So on the top, I have a cube root, and on the bottom, I have a cube root. And I'm going to look at those things separately. Cube root of 8, x to the 4th. 8 is actually a simple cube. What is that going to do? It's a cube root of 2. So I don't even have to make a factor tree there. And then, how many groups of 3 can I take out of 4? 1 is equal to 3, with 1 left over. Okay. Now, what about 27? Is that a perfect cube? Yes. So the cube root of 27 is 3. And then I just have a y, right? Do you have any questions? Alright. I think there might be one that I want you to practice on. We'll see. We're going to take a look at 11 and 12. 11 is a fraction, so I know I have to break that up into two separate cube roots. Again, remember your indices. So I have the cube root of a over the cube root of negative 27. Well, I know with a negative and a cube root, that's okay, so I'm just going to take it out. The cube root of a is just the cube root of a. I can't simplify it any further than that. Well, 27 is a perfect cube. I get 3. I already have a negative on the outside. So that's what you should get for number 11. Number 12. Again, I'm dealing with a fraction, a rather complicated one, but I'm going to deal with it one thing at a time. Numerator first, then denominator. So, cube root of 25, c to the 7th, d to the 3rd, over the cube root of 63. Now, the first one, 25. Well, if I look at 25, 25 is a perfect square, but it's definitely not a perfect cube, right? So I have to just leave it there. So I already know that I'm going to have a cube root of 25 still. I can't do anything with that 25. How many groups of 3 can I take out of cube root of 7? So I can take out, if I take 2 and then 1 left over, right? So I have c squared on the outside. And then I can take out 1 group of 3 for the d's, right? I still have my cube root of 25. And then, of course, if I were taking the test, I would see if this is a perfect cube by just doing 64 to the 1/3, and is it? Yeah, what is it? And that's that answer. Do you have questions on them? Yes. Do you have any other questions? Anybody on those cards? As always, Melissa. Okay. One more concept, then we're done for today. Rationalizing the denominator. I wouldn't write this down. I'm just going to talk about it. I would just say rationalizing the denominator cannot have a radical in the denominator. Just write that in big, bold letters somewhere. Cannot have a radical in the denominator. So there are several things that we don't like that make something unsimplified, and that is fractions often that aren't simplified. So we have to break those up. And then the radicands that we have to use factor trees for, get the product of primes, take out pairs, take out groups of 3, groups of 4, etc., depending on the indices. And we also really don't like radicals in the denominator. To get rid of the radical in the denominator, we have to do something called rationalizing the denominator. All that means is you're going to change the form of it. You can always change the form of something if you don't violate the mathematical rules that are in place. If I multiply by 1, don't I get the same thing? Sometimes, for example, let's say I have the number 4 and I multiply by 3 over 3. Well, 3 over 3 just reduces to 1, right? I'm just simply changing that form from 4 to 12 over 3, which reduces to 4, right? So these two are the same thing. One's just simplified and one's not. So that's what we're going to be doing. We're changing the form like we are there. So to change the form, I have to multiply by that denominator. So the square root of 3n over the square root of 3n. I'm not violating any rules here. I'm just changing the form of it by multiplying by a different way to write 1. So when I do that, on the top, I get, according to my product property, the square root of 5 times 3n, which is the square root of 15n, over the square root of 9n squared. What happens is you'll get a perfect square. So 9 is a perfect square, n squared is a perfect square, so you end up with 15n on the top over 3n on the bottom. So now you no longer have that radical in the denominator, because just by rationalizing, you're changing the form, so you get a perfect square on the bottom. And it goes away. Do you have any questions about that process? Does it make sense? The point is to get a perfect square on the bottom or a perfect cube, which we'll see in the next one. Alright, so on the next one, we're doing the same thing. We are rationalizing the denominator. Multiplying both the top and the bottom by the cube root of 9. So in the top, I have something on the outside, so I can't just automatically put it on the inside. I just have to leave it on the outside. And then on the bottom, my product property says that the cube root of 81 is 81 a perfect cube. It is. If you plug in your calculator, what do you get? Well, 3 times 3 is 9. 3 is 27. Huh? We're looking for a cube, a perfect cube. Is 81 a perfect cube? So, take your calculator. 81. Take your caret sign. And raise it to 1. So we have an issue here. We have 9 and 9, 81, 2. Oh, you know what we have to do? We have to break down 81. Okay, so if we run into a problem like this is what we have to do. We have to do a factor here. So you want to do a factor tree. Now, we have a couple issues here. If we take out one set of 3s, we end up with this. This is a little harder, okay? Let me be honest. So we have 2 cube root of 9. If we take out one set of 3s, we have 3, then we have a cube root of 3. Does that help? No. So what do you think we have to do? I have to leave the key root of 9 so I can cancel stuff out. Okay, so what that means instead is I can't have it in this form. I can't have it in this form. If on the top I have a key root of 9, then I have to have still a key root of 9. So I think there might be an issue here. The problem with the second one here is that you have to make it a perfect cube. Okay? So to make it a perfect cube, I know that 27 is a perfect cube, right? So really what I have to do is, in this particular case, I can't just multiply it by the cube root of 9 because I'll get the cube root of 81, that's not a perfect cube. So instead what I'm going to do is I'm going to think of the closest perfect cube I can think of to 9, which is going to be 27. 27 is actually a perfect cube, right? So I'll take 2 and I'll multiply it by the cube root of 3 and the cube root of 9. I'm going to multiply that by the cube root of 3 as well. I'm still multiplying by 1, it's just a different form of 1, right? So I still end up with 2, cube root of 3, because I can't simplify that. But now I have the cube root of 27. What's the cube root of 27? Right? Yeah. So you have 2, cube root of 3 over 3. So I guess what I would do when I approach these problems is I would say, if I multiply it by that denominator, will I get a perfect square or perfect cube? If I do, then I'm good. But if I don't, then I have to think of something else. Does that make sense? So there, when I multiplied by the cube root of 9 over the cube root of 9, I got the cube root of 81, which isn't a perfect cube, so I'm going to have to think of something else. So I think to myself, well, what is a perfect cube? Well, not 9, not 18, 27, right? So I just multiplied by cube root of 3 over cube root of 3. Does that make sense? Okay, sorry about that. So try that same approach to those next problems. Square root should be easy, because square roots will always work when you multiply by the denominator over the denominator, because you're multiplying by itself. And by definition, when you take the square root of something, you're getting that number where times itself, you end up with a perfect square. So that'll always work for square roots. With cube roots, it's different, and I apologize for that. But square roots, you just multiply by that denominator divided by the denominator. And then you see if you can simplify it any further, especially in the numerator here, which I cannot. So I leave it alone. That should cancel out the radical on the bottom, because you have a perfect square if you're multiplying it by itself. 16, same thing. Square root of 3 over square root of 3. You have a 9, which is a perfect square. This y squared, you take it out, so you have to continue to simplify. And then the 17, that's different. Because if you multiply by 32, you'll get a perfect square, you won't get a perfect cube, so you have to think about what is the closest perfect cube here that I can get. Well, I can get a 64 if I multiply it by 2. So I have to take the cube root of 2 over the cube root of 2 and multiply it. Does that make sense? And then you end up with 5 cube root of 2 over 4. Questions? You have several days to work on the next assignment. Work on the ones we've done so far. Save the rest for tomorrow's lesson. Oh, crap. Oh, darn it. Let me put that on there. Let me make the bell work. Thank you, Abby.